Yeah, thanks for inviting me. So probably some of you have already maybe attended a DRAMSys tutorial at DVCon. It was, I think, in 22, if I remember correctly. But this is 1.5 hours, and I cannot just compress that into 30 minutes. So I just take some key aspects that are probably relevant or interesting for you, also with respect to SystemC. So I try to show there the most important things and takeaways from more than 10 years using SystemC for DRAM simulation. So maybe start with DRAMSys in a nutshell. So probably you know it already. So it's a modern design space exploration framework for modern DRAM designs. And it helps you usually to answer the following questions. So which DRAM should I choose, which configuration? When should I support the next standard? How should I configure my memory controller? And what is actually the system level application behavior? So these are the typical questions where DRAMSys helps to answer them. And DRAMSys offers high speed and flexible models of all standards which are there. It's very fast and accurate compared especially to RTL. And then it helps you to identify bottlenecks in design pretty early. And of course, since it's SystemC TLM, you connect it to any core or interconnect that you have in SystemC, but also it's integrated into Gen 5, so you can use it natively also in Gen 5. Yeah, so we have a very interesting business model. So the simulator itself is open source, and we also release the well-known standards like DDR3, 4, LPDDR4, YDRO, and so on and so forth. And then for the new standards, there are some commercial licenses available. And with this money, we basically maintain the simulator. That's the main business model behind it. And such a license is also not that expensive. And we have many customers that are using DRAMSys, and when they license a standard, then they basically support the development and maintenance, which is done by Fraunhofer. Yeah. And if a new standard comes out, then we will open source the previous standard. So in a few days, hopefully we will have LPDDR6 out, and then LPDDR5 will also be open sourced soon. Yeah, and then we offer customer-specific consulting and modifications. So that's a little bit the business model behind it. Okay, so that is more the advertising block. And now let's have a look on how does actually DRAMSys work. And before we talk about that, we have to learn how DRAM memories work. And we saw already in the previous talk a little bit of how memories are usually assembled. And I just want to show that from a DRAM perspective. So DRAM was invented by Bob Dennard in 66. And it's basically just a transistor and a capacitor. And with that, he replaced basically the core memory. And now we have DRAMs, and the first DRAM from Intel was just 1024 bits. So how does it work? As I said, capacitor and access transistor. And this is one DRAM cell, which stores exactly 1 bit. And these DRAM cells we group in so-called subarrays. And we do that especially for having an efficient wiring. And these subarrays have usually a size of 512 times 512 or 1024 times 1024. And these subarrays we put then in banks. And then a DRAM usually has 8 up to 16 banks. And these banks could be used in parallel. But they share the same data and command bus. So it's not 100% parallel, but we have basically this bus bottleneck there. Yeah, and this is in red now circle, this is the DRAM bank. And you see a typical device here from Samsung. It looks pretty similar to this architecture. Okay, so how does it work now? So how can we access one single bit? So we have our subarray here. And then we have in the bank a DRAM row, which can be, for example, 1 kilobyte of size. Oh, sorry for that. And now we can send a so-called activate command, and this activates the primary sense amplifiers in this specific bank. And then on the subarray level, you see that these are the single bits here, and now a lot of bits are latched basically on this primary sense amplifier. And this is a necessary step, because then you restore basically the data which is in the capacitor, and then you amplify it directly. So this also amplifies the value which is written in the capacitor. Yeah, you can or activate several banks in parallel. That's what I mentioned already before. So you could also activate P4 and P7 in this case. And then if you want to perform a read operation, for example, then the read consists basically of two parts. First part is basically the column latency. And this is happening now. So I send a read command, and then some parts of this 1 kilobyte are basically latched in a secondary sense amplifier. And these are just 64 bits. And these 64 bits will now be bursted out. So we have 64 bits in this buffer here, and the interface width of this DRAM chip is by 8. That means we have to divide this data into 8 packets, and this is the second part of the read, which is the burst, and then we pipe this out. So this is basically how DRAM works. And if you want to close a DRAM row, then we have the so-called pre-charge command, which again brings the bit lines to VDD half as a reference voltage. And the last thing which is important is the refresh. So we have leaky capacitors. So from time to time, we have to go through the DRAM. Usually every 7.8 microseconds, we have to refresh a row. And this we do basically, so in 64 milliseconds, we can refresh all the rows in the DRAM. And this also is bad for the performance, because doing a refresh, we cannot really do any access. Okay, so these are the basic DRAM operations you learned now. So we have activates, we have reads, we have pre-charges, and you see this is, we need to meet their specific timing dependencies, because all these processes take time. So you see that when we do an activate, it takes some time until we have latched the data into the primary sense amplifiers. So this is basically what you see here. So you send an activate command on the bus, and then you have to wait TRCD, the row to column delay, and then you are allowed to send the read command. But if you send the read command, you don't get the data on the data bus immediately or the cycle after. We have to wait this column latency, because we have to get these 64 bits down to the secondary sense amplifiers. And if it's there, then we can burst out the data. So this is what happens basically then here. And then you see already, okay, you cannot send the next read command right after this read command. So you have to put here a knob. Because if you would do that, then this data that belongs to the second read here would overlap with the data previous on the data bus. So between reads, you have to wait a TCCD, which is the column to column delay. So when you access 2 columns in a row, you have to wait basically some time. And also this has to be, of course, fulfilled here. And there are many more timings. I will talk about timings also later, because this is very important when we model the DRAM device. But you can already imagine that this has some kind of complexity, and this is just an artificial DRAM. It's in reality much more complex. Yeah, so DRAMSys as architecture, it's basically TLM2 compliant, and we are using the AT coding style. Since we want to have very accurate results that are matching with RTL, so we want to have cycle accurate results, and we could get, from a timing perspective, we could get cycle accurate results, and I show you today how we reach that. And that's a very flexible architecture. So everything here is TLM2 AT. So you can just put some other components in between. And we do that also from time to time in our research. So we put just another component here to do something. And also here in front, everything is TLM-80. But here in the back, between the DRAM channel controller that implements this protocol that I showed you before, and the DRAM itself, there we have a custom TLM protocol, which we call DRAM-80. And I want to show you also how that works. So how do we get the speed up in DRAMSys? The idea is we just simulate only the events that are really important. So we do not simulate any clock signals because the clock signal has the highest event generation rate. This would make everything pretty slow. But do we really need to simulate each and every clock cycle? So this is now, I think, an example from a DDR memory. So you send the activate command, and then you have to wait a long time here, trcd, until you are allowed to send the read command. And an RTL simulator would probably then just simulate all these knobs, but nothing really happens. And this is what we don't do. So we just concentrate on the important events. The event is basically when the activate command is issued. And we just simulate in this TLM way, just a begin activate and an end activate. And this is where we get the speed up. Yeah, so we can skip idle clock cycles, and we have a large event reduction, especially at low memory access densities, but we have no loss of accuracy. So from a timing perspective, DRAMSys gives you the same results as an RTL model, but for that we need a lot of math in the background to calculate the correct times. And I want to talk about this also in a minute. Yeah, so how does it look like? This is the typical way how we show that. So we don't use message sequence charts or something like that. So we use this way. So this is a begin request, an end request, and there's the begin response and end response. This is what you see on the input of the DRAM controller. And here you can see what happens on these DRAM banks in parallel. And this is also the view that we use in our debugging and analysis tool, which we call Trace Analyzer. And there you see again also the timing. So for example, here's an activate to a bank. This just takes here now 2 cycles. And then we send the read command here. So the begin of the read is here and the end of the read is there. And then implicitly, we don't simulate the command bus. We don't simulate the data bus. This is what we know implicitly, basically. We know that there is a read command. And since we can schedule the next request here, the yellow one, we could already schedule the activate, but we cannot schedule it here because this cycle is already occupied. So we have to postpone it by 1 cycle. And you see that things can now happen out of order. Yeah, so the yellow one, in this case, is probably not that much out of order, but you could imagine that things can get highly out of order, and therefore we need also the approximately timed coding style. Yeah, so we have to track a lot of things like these timings, and also if the command bus is occupied. So you can already imagine that in our model, it's not that easy because we don't have a state machine that is clocked. So we have something different, and I want to show you also how we do that. So let's look on the speed. In this figure, we just compared against an RTL model. So that's the baseline. And then we have executed here several traces that have a different memory access density. So that 100% here means I want to have basically each and every clock cycle, I want to get something out of the DRAM. So we want to have 100% bandwidth. Here we have 10% bandwidth, 1%, 0.1, and so on and so forth. And you could also implement a DRAM simulator, which is using clock cycles, but not in RTL. So we can just write a C++ state machine based simulator that is also clocked, and you see that this follows more or less also the baseline of the RTL. So you don't get much speed up. But if you use this TLM approach, you skip very often clock cycles. And there you could get speed ups up to 10x. But this depends on the trace density. But usually your application always jumps around here. So sometimes you have a number crunching phase, then you are there, and then DRAMSys is not blocking at all the simulation or not slowing it down. But then you get a more memory intensive phase in your application, and then DRAMSys will be a little bit slower because the number of events increases. So for typical applications, we see a speed up of 400x compared to RTL, but we are still 100% accurate. And now the question is how we go there. And when I started with DRAMSys, my first model was wide I/O because I did my PhD mainly on wide I/O DRAMs. And then I want to compare wide I/O against something else, and the something else was DDR3. So I wrote first in SystemC a wide I/O model, and then I wrote a DDR3 model. And that was around 2012, 2013, basically, when wide I/O came up. And then later on, we need more comparison. We added a DDR4 model and so on and so forth. But it was always a lot of hand coding work, and it was error prone. So when a new standard comes out, it took me a long time to adapt it because I had to change the whole concept of DRAMSys all the time. And from that, I learned we need something more clever. If a new standard comes out, then I want to be faster there with my code, and it should not have any errors. And that was basically the idea. Can we get from the standard somehow into something which is more formal, where we could generate the code? And yeah, some words about the standards itself now. This is really complex. So in DDR3, we have just 226 pages, and about 100 pages are just timing diagrams of these timings that I showed you, because there are many more. It's not just the 5 timings that I showed you. And DDR5, we have already 500 pages. So I assume if DDR6 comes out, we have to deal with 700 or even 1,000 pages of timing diagrams. And these descriptions in the standards, they are not really formal. It's just sketches, pictures, and graphs. And they are even not correct. I just want to give you a brief example. This is the state machine that describes the protocol. And JEDEC even says, okay, this is a simplified state diagram intended to provide an overview of the possible state transitions and the commands to control them. But it's only for one bank, and more stuff is not captured in full detail. So that's not really helpful. So we have only one bank. And then we have states in this diagram that do not actually exist. In some states, we even have twice, which is a little bit ambitious. Actually, we only have in this diagram really these 5 states. So a bank is active or it's inactive, or we are in power down or in self-refresh or in another power down. The rest are just commands that are executed. And yeah, 2 commands we even have twice, and also some inconsistencies in that. I don't want to go so much into detail about that. But what the standard gives us is not really something that is formal. So then I thought, okay, we need a comprehensive and mathematical model of DRAM states and commands and timing. And then I remembered my lectures about system modeling, and I came up with an idea. So the ideal case would be that we have a formal language which has the power to basically compress 100 pages of timing diagrams into one single page in a domain-specific language. And yeah, right now a new standard comes out, and then I have to write my whole SystemC code again, and then I have to simulate so long until I'm convinced that it's error-free. But sometimes you misinterpret maybe a timing diagram in the standard, and when you code, and that would not be a good thing. So the idea is we want to be faster. So if a new standard comes out, 1 week later, I want to have the model. Yeah? So that was my goal. And then I remembered my undergrad's lectures where I learned about Petri nets. So I'm not sure if you are 100% familiar with that, but Petri nets are pretty cool in order to model concurrency. And a DRAM is highly concurrent. So if we have 16 or 32 banks, all these banks are doing things concurrently. And yeah, Petri nets are pretty good in that to capture this, because when you model that with state machines, you would get a state explosion. In Petri nets, they don't explode if you model just the commands. Let's talk about timing later. So here you see basically the main Petri net. So we have here the idle state, and here you see if in this state a token goes to this place, then this bank is active. And if this bank is active, you are allowed to send different DRAM commands. I don't want to go so much into the detail because you can read that also in our papers. But this is a comprehensive model that separates states and commands. And it's not mixing that as the state machine that we saw before. And there you see again also our 5 state types that are modeled now with these places. And we can support multiple banks in one model. And the whole thing is divided in several subnets. And then we can also handle these power down modes and all of this. Okay, so that was the idea. So that the semantic of our domain-specific language is basically based on these Petri nets. But this is only the structure of the DRAM and what commands can you send and what is allowed. So can I, for example, we have here these inhibitor arcs. They make sure that you don't activate one bank twice, for example. So if this bank is active, you cannot activate it anymore. So it also holds the valid transitions, and these are checked basically. But timing is the other thing, and there we looked in the literature, is there a way to model timing in Petri nets? And yes, there is. So you could use a construct like this, which is here just this simple arc then. That tells basically, okay, if you send this DRAM command here, then the next DRAM command that you could send is inhibited by this amount of time here. So you have to wait tx until you can execute tau2 here. That's the main idea, or the semantics of that. So for example, if we look again here, activate and read, we have to wait this trcd command. And this is what we would describe with that. So if you put that in this toy example here with just 2 banks, which is an artificial DRAM that does not exist, so DRAMs usually have at least 8 banks, you see already the complexity of these timings. And if we go now to a DRAM that has 8 banks, the graph looks like this. So I think now you understand how complex this timing protocol is. And therefore, it's really error prone if you write all this code by hand. And that was the idea. We have now this Petri net semantics, and now put that in a domain-specific language, which we call DRAM-ML. And this is a domain-specific language to describe the DRAM's behavior and also the timing. And this DSL is then the basis for a correct by construction SystemC code generation. So how does it work? If a standard comes out, then we will read it, we will understand it, and then we write down basically the behavior of these timing diagrams and all the dependencies in our DSL. And this DSL is written in Python. And in Python, we also have a generator then that generates the SystemC code that makes sure that we fulfill all these timings, so-called timing checkers. And for that, we use the templating engine Ginger to generate the SystemC code. And this SystemC code then we include into the DRAMSys simulator. And first time we did that for the DDR5 release. And it took us just 1 week to do this step and to the generation, and then another week to implement other things in the memory controller. So we are pretty fast in creating a new model. Yeah, and this is how the code looks like. So these are basically 100 pages of timing diagrams compressed then in 122 lines of code. Yeah, just that you can imagine how large this compression is, basically. And there you can see then how we have here timing constraints for specific bank, and between this command and this command we have to fulfill this timing between whereas the read and act and read we have to have this TRCD and so on and so forth. Yeah, so you can see that we can highly compress all these requirements from the JEDEC standard just in some lines of code with our DSL. Yeah, the next thing is the trace analyzer. That's also part of DRAMSys, and this is pretty helpful to see and understand what's going on in the DRAM system. I can also show you in a second that live. And there we have some additional things, like we have a Python interface, and we can record all the transactions during the simulation. And everything is stored in a SQLite database. And then we can run very simple queries on that. And you can write matrix. So you just put there a matrix decorator, and then this also appears here in the trace analyzer. And then you can compute things like what is the average response latency, what's the median response latency. But you could also follow the bandwidth over time. You can do bandwidth versus latency plots and a lot of things. So this is basically what's happening in the trace analyzer. So I just look if I have my virtual machine here. So you can just run a DRAMSys simulation. This is now a very simple setup here. In the beginning, you see the address mapping that is used. And then at the end of the simulation, you can also see already some statistics, like the bandwidth, average bandwidth, or the maximum bandwidth that could be achieved. And then you could start the trace analyzer, which is written in Qt. And there you could now see, if you zoom out a bit. So, by the way, these boxes are clock cycles. But as you know, we don't simulate clock cycles. But of course, all the transactions are aligned to the clock cycles. And then you can really see what's going on in the DRAM. You see your begin requests and end requests, end responses. And then you see also what's going on in the bank. So right now, this is not a really good usage of the DRAM because you don't exploit the bank parallelism, which is there. But you could scroll a little bit further. There you see there are a lot of row misses right now, and you see also that the bandwidth is not that great. So you can pretty fast go through these traces and understand what's going on in your DRAM system. So for example, this is a refresh where you see that your bandwidth drops to 0, so no data on the data bus anymore. And yeah, as I said, then you can run, for example, these matrix scripts. So maybe I should not run everything. So maybe just average response latency, for example. There you can see then the average response latency. But there are some more things, especially if you want to understand what's going on in the memory. You could look, for example, for dependency analysis. And if you click then click more, probably. Okay, this somehow doesn't work right now. I don't know why, but usually it shows you then the dependencies, these timing dependencies you can then see here as in this diagram. But I'm surprised. Usually that works when in the demo, but probably I have configured the wrong memory device. But there are some other things like latency analysis. So you can have a look here on the histogram. You can understand which transactions are here the outliers. So this is the transaction that has the highest latency, and then you can go there and you can understand why this is the case. This is because I think of a long refresh block that happens here. So it's actually a pretty powerful tool. Yeah. Okay, that brings me already to the last slide. So if you are interested in that, yeah, fork us on GitHub. Yeah, you also can find it in DRAM 5. And we have also DRAM power simulator, where I have no time today to talk about that. But we can even do then thermal simulations of the memory device, which is also sometimes pretty interesting. Okay, that's it. Yeah, I hope you got an idea about DRAMSys, and now I'm open for questions.
Thank you very much indeed. I think we've all learned more about DRAM in the last half an hour than I've ever known before. Are there any questions?
Yeah, Matthias, how do you check the cycle accuracy of your model?
Yeah, so basically we don't have to check it afterwards somehow because we make sure that's basically correct by construction. That's the most important thing. So as long we do not make an error here in this path, the code that comes out is correct, basically. Also, of course, the generator has to be correct. But we do a lot of testing here that we are pretty sure that that what we generate here as source code is 100% JEDEC compliant, and from that, then we know, okay, we are cycle accurate. Does that help?
Yeah, somehow.
So that's
I guess the question is, can you test this against hardware, right? I mean, in a way, you do have a DDR in the computer you're on.
Yeah,
right?
So there are also some other degrees of freedom, right? So that depends also a little bit on the behavior of the memory controller. So we are JEDEC compliant, but this controller has, for example, a scheduler, and we have a large set of algorithms for scheduling that you could choose. But if you have now, for example, a Synopsys DesignWare IP, this IP has a specific scheduler, and depending on that scheduler, maybe the result is different. But if we would model the same scheduler in our TLM model here, then we would also get the same cycle accurate results. Yeah. So what we have is a very generic controller that fulfills usually the needs of our customers, yeah, and also for researchers. But of course, if you want to have a very specific IP, then you would need to build your custom DRAMSys that has the same algorithms as your IP.
Yeah, there's no point in hooking. Yeah, if you've got an RTL DRAM control, there's absolutely no point to DRAMSys, because then we're all at RTL and there is little.
Yeah, but what we did already, we put here transactors, and then we put an RTL controller at this place. Also that we did already in the past, and also that worked. Yeah, and then we did basically back-to-back simulations and compared the things. So there we can basically tune our DRAMSys model to a specific IP.
In view of time, it looks like we're up against it. So I thank you very much indeed for the presentation. That's been absolutely brilliant. If there are other questions or comments, then please be directly in touch with Matthias.
Yeah, so just write me an email. So if you Google me, you will find me.
Not that hard to find. Okay, thank you very much indeed.